The global electrical grid is often described as the largest and most complex single machine ever constructed by human engineering, an interconnected organism that breathes energy across entire continents to sustain modern civilization.
Yet the physical transportation of electricity across space is inherently fraught with friction.
The fundamental purpose of this vast network remains the same today as it was over a century ago. Moving massive quantities of energy from the remote locations where it is generated to the densely populated urban and industrial centers where it is consumed. However, the silent, invisible battle taking place within every inch of electrical conductor on the planet is the relentless fight against electrical resistance.
To visualize the immense engineering challenge of power transmission, one must imagine the catastrophic energy loss that would occur if we attempted to push electricity across hundreds of kilometers using the standard alternating current voltages found in residential wall outlets.
All conductive materials, including the highly refined aluminum and copper used in global transmission infrastructure, possess a natural atomic resistance to the flow of electrons. As electrons are forced through the metallic lattice of a wire, they continuously collide with the metal atoms. This subatomic friction manifests entirely as heat, draining vital energy from the circuit and dissipating it uselessly into the surrounding atmosphere.
The rate at which this energy is lost to heat is governed by a fundamental principle of physics known as Joule's law of heating. This law dictates that the power lost to resistive heating is directly proportional to the resistance of the conductive wire multiplied by the square of the electrical current flowing through it.
Because the power loss increases exponentially with the current, pushing a massive volume of electrons, a high current, through a long-distance wire results in thermal losses so severe that the conductor could physically melt, leaving virtually no usable energy to reach the destination. It is precisely for this reason that long-distance transmission at low voltages is physically impossible and economically disastrous.
The engineering solution to this limitation relies on an elegant inverse relationship between voltage and current. The total electrical power delivered through a transmission line is the product of the voltage, which can be conceptualized as the electrical pressure, and the current, which represents the volume of flowing electrons. To deliver the exact same amount of total power to a distant city, engineers can dramatically increase the electrical pressure while proportionally decreasing the volume of the flow.
If the voltage is doubled, the current is cut in half. Because the resistive heat loss is tied to the square of the current, cutting the current in half reduces the wasted heat by a factor of 4. By stepping up the voltage to hundreds of thousands of volts, the current is reduced to a mere fraction of its original magnitude, allowing immense amounts of energy to glide across vast continental distances with minimal thermal friction and minimal energy bleed.
This inverse relationship was not always universally accepted, and it was the central point of contention during the historic War of the Currents in the late 19th century. Thomas Edison famously championed direct current, a system that was highly stable but could not easily have its voltage altered.
Because Edison's system transmitted electricity at the same low voltage used by light bulbs, the massive current resulted in extreme heat losses, limiting the range of his power stations to a mere mile or two, and requiring power plants to be built in the center of every neighborhood. In contrast, Nikola Tesla and the industrialist George Westinghouse pioneered alternating current, a revolutionary system that allowed voltage to be easily stepped up for efficient long-distance transmission and safely stepped back down for household use. The absolute supremacy of high-voltage alternating current was conclusively demonstrated on a macroscopic scale during the historic 1891 International Electrotechnical Exhibition. During this event, a team of visionary engineers, including Oscar von Miller and Mikhail Dolivo-Dobrovolsky, successfully transmitted three-phase alternating current at a frequency of 40 Hz over a distance of 175 kilometers. The electricity originated from a hydroelectric generator in Laufenau am Neckar. passed through an Oerlikon transformer to boost its pressure, and traveled to the city of Frankfurt, where it powered an awe-inspiring artificial waterfall and a sea of incandescent light bulbs. Operating at roughly 75% efficiency, this monumental demonstration proved that high-voltage transmission could conquer geographic distance, effectively ending the war of the currents and forging the architectural foundation of the modern power grid.
In the contemporary landscape of 2026, the imperative to minimize transmission losses is more critical than at any previous point in human history. The global energy ecosystem is undergoing a radical, decentralized transformation. Historically, the grid relied on a centralized model, where massive coal or nuclear plants were constructed relatively close to the urban or industrial hubs they served.
Today, the aggressive pursuit of decarbonization has fundamentally altered the geographic distribution of energy generation. Generation assets are increasingly located in incredibly remote regions where natural resources are most abundant, such as massive offshore wind farms in the treacherous waters of the North Sea, or sprawling solar photovoltaic arrays in the deep deserts of the American Southwest and North Africa. Simultaneously, electricity demand is experiencing a structural resurgence after years of plateau driven by the mass adoption of electric vehicles, the electrification of industrial heating, and the explosive, energy-intensive growth of artificial intelligence data centers. The European grid alone requires an estimated 1.4 trillion euros in investments by 2035 to handle this bidirectional, decentralized flow of power. Consequently, modern transmission lines must act as ultra-efficient continental highways, bridging the expanding geographic chasm between isolated renewable energy sources and ravenous urban demand centers. Without the sophisticated manipulation of voltage and current, the entire paradigm of the global green energy transition would collapse under the weight of its own thermodynamic inefficiencies.
The crucial mechanism that enables this delicate manipulation of voltage and current is the electrical substation, a highly fortified industrial compound that acts as the gateway between the power plant and the open transmission highway. Immediately after electricity is generated, whether by the spinning turbine of a hydroelectric dam or the inversion of direct current from a solar farm, it exists at a relatively moderate generation voltage, typically between 5 and 35 kilovolts.
Before it can be efficiently dispatched across the country, it must be routed through a step-up transformer, which is arguably the most vital piece of equipment in the entire power transmission hierarchy. A step-up transformer operates entirely on the principles of electromagnetic induction, a profound physical phenomenon discovered by Michael Faraday in 1831. The device is remarkably elegant, lacking moving mechanical parts, yet it is capable of transferring immense amounts of energy across physically separated circuits. Within the heavy steel tank of the transformer, the incoming alternating current flows through a primary coil composed of thick, highly conductive copper wire. As the alternating current surges back and forth through this primary coil, reversing direction dozens of times a second, it generates a continuously expanding and collapsing magnetic field. This highly dynamic magnetic flux is captured and channeled by a massive core constructed from laminated sheets of specialized iron or silicon steel.
The magnetic flux is directed through the iron core and allowed to intersect with a secondary coil of copper wire located a short distance away. The changing magnetic field literally pulls and pushes the electrons within the secondary wire, inducing a voltage across the secondary coil and transferring the electrical energy without any physical metallic connection between the input and the output. The transformative magic of the device relies entirely on the ratio of the wire turns between the two coils.
In a step-up configuration, the secondary winding features a significantly greater number of turns than the primary winding. As the invisible magnetic field sweeps across this dense concentration of secondary turns, it induces a proportionately higher voltage, successfully stepping up the electrical pressure to hundreds of kilovolts, while simultaneously forcing a reduction in the current to balance the total energy equation.
The sheer physical forces at play within these massive units profoundly alter the surrounding sensory environment. To stand inside a high-voltage substation is to experience the intense, visceral reality of electricity at an industrial scale. The air is permeated by a continuous, monotonous buzzing or humming noise known as mains hum, which typically resonates at the grid's fundamental frequency of 50 or 60 Hz.
This auditory signature is not a malfunction, but a result of a physical phenomenon known as magnetostriction. As the alternating magnetic fields surge through the transformer's ferromagnetic core, the metallic structure minutely expands and contracts at a microscopic level, creating physical vibrations that transmit through the cooling oil and the steel casing into the surrounding air.
The intensity of this hum is directly proportional to the applied voltage, serving as a constant acoustic reminder of the immense pressures being contained within. The philosopher and composer John Cage once visited an anechoic chamber at Harvard University to experience absolute silence, only to hear a high-pitched sound and a low-pitched hum.
He was informed that he was hearing his own nervous system in operation and his blood in circulation. In much the same way, the persistent low-frequency drone of a high-voltage transformer is the sound of the electrical grid's own circulatory system in operation, vibrating with the raw energy required to sustain modern life. Once the electrons have been pressurized to extra high voltage, often ranging from 230 to 765 kilovolts, the energy flows out of the transformer and into the broader architecture of the switchyard. The power is first routed onto a main bus bar, which acts as a heavy-duty central circulatory system made of thick aluminum or copper tubing. From the bus bar, the power is distributed into the individual transmission lines, but it must first pass through an array of sophisticated safety mechanisms, most notably the high-voltage circuit breakers and disconnect switches.
Circuit breakers are monumental safety valves designed to instantly sever the connection to the grid if a catastrophic fault, such as a lightning strike or a fallen tree, causes a sudden, dangerous surge of fault current. Interrupting a circuit at several 100,000 volts is a monumental physics challenge.
The moment the internal metallic contacts of the breaker pull apart to stop the current, the extreme voltage simply tears electrons from the surrounding molecules, creating a superheated plasma arc that bridges the physical gap, allowing the electricity to continue flowing. Historically, grid operators solved this by flooding the breaker chambers with sulfur hexafluoride, a highly stable, non-flammable gas with exceptional insulating and arc-quenching properties. However, sulfur hexafluoride is a uniquely devastating greenhouse gas, possessing a global warming potential more than 24,000 times greater than that of carbon dioxide. As part of the 2026 decarbonization mandate, the industry is undergoing a massive paradigm shift to eliminate these fluorinated gases from the grid infrastructure entirely. Modern substations are now actively deploying advanced vacuum circuit breakers and clean air switchgear.
In these cutting-edge vacuum interrupters, the contacts separate inside a hermetically sealed chamber maintained at an extreme vacuum. Because there is virtually no gaseous matter present to be ionized into plasma, the arc is instantly starved and extinguished the very microsecond the alternating current crosses its natural zero point, guaranteeing immediate and environmentally pristine circuit isolation.
As the newly pressurized electrical energy departs the highly controlled environment of the substation, it enters the overhead transmission lines, embarking on a cross-continental journey exposed to the open elements. Here, the transmission system engages in a continuous dynamic interaction with the atmosphere itself. Because high-voltage lines do not possess a rubber or plastic insulating jacket, such insulation would melt under the thermal stress and add impossible weight to the suspended cables. The raw, energized metal is completely exposed, utilizing the surrounding ambient air as its sole dielectric insulator. However, air is only an effective insulator up to a certain threshold. As the voltage carried by the conductor increases, the invisible electrostatic field radiating from the surface of the wire becomes intensely concentrated. if the strength of this localized electric field gradient exceeds the natural dielectric strength of the air, which is approximately 30 kilovolts per centimeter under dry standard conditions, a fascinating and problematic physical breakdown occurs.
The extreme electrical pressure forcibly strips electrons from the adjacent nitrogen and oxygen molecules, transforming the surrounding layer of air into a conductive, self-sustaining plasma.
This phenomenon is known as corona discharge. When a transmission line enters a state of corona, it begins to continuously bleed electrical charge directly into the atmosphere, representing a significant and economically costly waste of energy for utility companies. To an observer standing beneath the lines, corona discharge makes its presence known through distinct sensory signals. It generates a continuous, erratic buzzing, crackling, or hissing noise that is entirely separate from the deep hum of a transformer.
During the night, the ionized air emits a faint, eerie bluish or purplish glow that hugs the contours of the wire. The phenomenon is highly sensitive to meteorological variables. Heavy fog, high humidity, or the onset of rain dramatically increases the conductivity of the air, significantly amplifying both the intensity of the discharge and the volume of the crackling noise. In essence, the hissing of a power line during a rainstorm is the sound of thousands of miniature, continuous lightning strikes ionizing the moisture in the air. To engineer a defense against this atmospheric energy leak, physicists and utility engineers deploy a specialized structural configuration known as bundled conductors. The intensity of the electrostatic field surrounding a wire is inversely proportional to the radius of that wire. A thicker cable spreads the electrical stress over a larger surface area, reducing the peak field intensity.
However, manufacturing and suspending a single gigantic solid metal cable thick enough to prevent corona discharge on a 500 kilovolt line would be mechanically unfeasible due to the immense weight and total lack of flexibility.
Instead, engineers split the single electrical phase into a bundle of multiple smaller subconductors, usually 2, 3, 4, or even 8 separate cables, arranged in a precise geometric pattern, such as a square or a hexagon. These subconductors are held firmly apart at uniform distances by rigid, non-conductive mechanical devices known as spacers. By forcing the wires to operate in parallel with empty air gaps between them, the bundled configuration artificially increases the effective geometric radius of the entire assembly.
This brilliant manipulation of geometry dramatically reduces the surface voltage gradient across the entire bundle, pushing the electric field intensity safely below the ionization threshold of the air, thereby suppressing corona discharge, mitigating radio frequency interference, and improving the thermal dissipation of the line.
Further atmospheric mitigation occurs at the hardware level. Wherever there are sharp mechanical angles, such as the mounting hardware or the ends of insulator strings, the electric field naturally concentrates and spikes. To smooth out these dangerous stress points, engineers install anti-corona rings, which are smooth, toroidal metallic tubes that enclose the sharp joints. By increasing the radius of curvature at these critical junctions, the grading rings gently distribute the electrical field, lowering the peak intensity and further preventing the atmospheric breakdown. This atmospheric struggle also dictates the massive scale and distinct visual aesthetic of the transmission towers themselves. Because the lines are carrying lethal amounts of energy and relying solely on the air gap for insulation, the towers must provide immense physical clearances.
If an extra high voltage wire were to swing too close to the ground, to an underlying tree, or to the steel body of the tower itself, the dielectric strength of the air would fail instantly, resulting in a catastrophic explosive arc flash that would cause massive damage and trigger immediate protective shutdowns across the grid.
Therefore, the sprawling lattice steel towers, often exceeding 50 meters in height and spanning hundreds of meters between supports, are explicitly engineered to maintain vast pockets of insulating air under all possible environmental conditions, serving as the skeletal framework that holds the raw, surging power safely out of reach.
The height and placement of these energized lines introduce another layer of environmental complexity: the interaction with avian species. Large birds, particularly raptors like golden eagles and ferruginous hawks, are naturally drawn to the towering vantage points provided by transmission structures for hunting and nesting.
However, this attraction is perilous. Electrocution occurs when a bird with a large wingspan simultaneously touches two energized conductors, or touches one energized conductor and a grounded metal component of the tower, completing the electrical circuit through its body.
To mitigate this fatal risk and prevent the power outages and wildfires caused by these thermal events, utilities engage in rigorous bird-safe engineering. Engineers increase the physical spacing between the phases to exceed the maximum wingspan of local raptor populations. To prevent birds from colliding with the thin, hard-to-see overhead ground wires during flight, brightly colored bird flight diverters are clamped onto the lines, greatly increasing their visibility. Furthermore, because removing massive nests built of conductive sticks is a constant maintenance challenge, progressive utility companies actively construct dedicated nesting platforms on safe, unenergized sections of the towers. This proactive approach provides eagles and ospreys with secure habitats while preserving the integrity of the high-voltage infrastructure.
The physical deployment of these lattice towers and suspended cables initiates a grueling battle against the mechanical forces of nature, requiring a meticulous balancing act of structural engineering, material science, and environmental management. A transmission line is far from static. It is a highly dynamic structure forced to endure decades of severe stress while crossing diverse terrains ranging from sub-zero mountain passes to scorching desert highways. The primary mechanical adversaries of the overhead line are extreme wind loads and ice accumulation. Transmission towers, constructed from bolted angular steel sections to maximize the strength-to-weight ratio, are designed to remain rigid during hurricane-force gusts. However, the cables suspended between them act like massive sails. During severe winter storms, supercooled rain can coat the conductors in thick sheafs of heavy, solid ice. This radically alters the aerodynamic profile of the cable, transforming it from a smooth cylinder into an irregular teardrop shape. When high winds strike this ice-laden profile, it can induce a violent, low-frequency oscillation known as galloping, where the cables bounce wildly in the air, creating mechanical forces strong enough to rip the steel arms directly off the towers. To dampen these destructive vibrations, engineers attach weighted, spring-loaded mechanisms called stock-bridge dampers to the cables near the suspension points, which absorb the kinetic energy of the wind and prevent the resonant frequencies from tearing the infrastructure apart. An equally persistent challenge is thermal expansion. The most common cables used on global grids are aluminum conductor steel reinforced lines, which combine an outer layer of highly conductive, lightweight aluminum strands with an inner core of high-tensile steel to provide structural backbone. When the grid is operating at peak capacity and massive currents flow through the lines, the intrinsic resistance of the aluminum generates internal heat. During the height of summer, this internal heat is compounded by direct solar radiation, causing the metallic lattice of the cables to physically expand and elongate. As the wire stretches, it sags downward between the towers. If a line sags too deeply, it violates the minimum ground clearance requirements mandated by safety regulations, risking a deadly short circuit to the earth or the canopy below. Because of this thermal vulnerability, the initial installation of the wires, known as the stringing and sagging operation, requires absolute precision. The process often begins with highly skilled helicopter pilots flying specifically modified lightweight helicopters like the MD-530F Littlebird, who carefully thread a small, temporary pilot line through the suspension pulleys. known as stringing blocks, positioned on the top of each tower.
Once the pilot line traverses a treacherous valley or a busy highway, heavy-duty hydraulic pullers and massive bull-wheel tensioners stationed on the ground take over. These machines winch the permanent, heavy transmission cables through the blocks under immense physical tension.
Engineers must calculate the exact tension required so that the line maintains a precise geometric curve, ensuring that even under maximum thermal expansion during the hottest day of the year at maximum electrical load, the sag will remain safely above the ground. Securing these highly tensioned, energized cables to the grounded steel towers requires remarkable insulating technology. The cables do not touch the towers directly. They hang from elaborate assemblies called insulators. For decades, these were exclusively manufactured from toughened glass or heavy porcelain. But the modern grid relies increasingly on advanced polymer composite materials, such as silicone rubber and cycloaliphatic epoxies. These insulators are sculpted into a series of ribbed, umbrella-like discs known as sheds or bells. This rippled design is a masterclass in electrical engineering. By forcing any electrical leakage current to travel up and down the contours of every shed, the design vastly increases the creepage distance, the total surface path between the live wire and the grounded tower, without increasing the overall length of the assembly. Furthermore, the overhanging bells ensure that during severe rainstorms, the undersides of the sheds remain completely dry. This prevents the formation of a continuous, unbroken path of conductive water that would allow the voltage to flash over and short out the system. The hydrophobic nature of modern silicone polymers further forces water to bead up and roll off, making them exceptionally resilient, even in environments plagued by heavy coastal salt spray or dense industrial pollution. Maintaining this precarious infrastructure is among the most hazardous professions on Earth, with electrocution and falls presenting constant dangers. To minimize downtime and avoid interrupting the power supply to millions of people, highly specialized linemen frequently perform live-line bare-hand maintenance. Transported by helicopters or insulated bucket trucks directly to the cables, these technicians work on the wires while hundreds of thousands of volts continue to flow. To survive, the linemen wear a Faraday suit, a specialized garment woven with fire-retardant fabric and highly conductive microscopic metallic threads. Before making contact with the wire, the suit is electrically bonded to the energized conductor. This instantaneously equalizes the worker's body to the exact electrical potential of the power line, much like a bird landing safely on a wire. Because there is no difference in voltage across the worker's body, the electricity simply flows around them through the highly conductive suit, treating the human inside as an empty void and allowing the technician to manually repair the energized components with absolute safety. Simultaneously, utility companies must manage the immense ecological footprint beneath these towering structures. The long, linear corridors carved through forests and landscapes for transmission rights-of-way are managed using a sophisticated approach known as integrated vegetation management. Rather than continually clear-cutting or applying indiscriminate broadcast herbicides that devastate the ecosystem, arborists strategically use selective treatments to permanently remove tall, deep-rooted tree species that threaten to grow into the power lines and cause outages. This selective removal opens the forest canopy, allowing sunlight to reach the soil and stimulating the growth of low-profile native shrubs, ferns, and wildflowers. Over time, this deliberate ecological suppression arrests the natural succession of the forest, transforming the right-of-way into a thriving, continuous, early successional meadow. These corridors have become unintended sanctuaries for biodiversity, providing crucial habitat and migration pathways for wild bees, rare butterfly populations, and threatened shrubland birds, such as the prairie warbler and yellow-breasted chat, that have otherwise lost their natural environments to urban sprawl and agricultural development. While the physical wires traverse the landscape, the electrical current within them dances to a rigorous, inescapable rhythm. The entire alternating current network of a continent operates not as a collection of independent power plants, but as a single, perfectly synchronized, massively complex machine. In North America, the electrical current reverses direction exactly 60 times every second, while in Europe and much of Asia, it oscillates at 50 times per second. This precise oscillation is the utility frequency, the fundamental heartbeat of the grid, and every single generator, motor, and transformer connected to the network must march in absolute lockstep with this global pulse. Maintaining this perfect synchronization is the supreme daily challenge of grid system operators. Deep inside secure, heavily monitored control rooms, teams of dispatchers, meteorologists, and power engineers watch vast digital maps of the grid, tracking the continuous, real-time tug-of-war between power generation and consumer demand. Often working arduous 12-hour DuPont schedules, these operators bear the immense responsibility of keeping the lights on for millions of people. The frequency of the grid is the direct physical manifestation of the balance between supply and demand. If millions of citizens suddenly turn on electric heaters or plug in electric vehicles during a winter evening, the massive increase in electrical demand acts as a physical drag on the spinning generators at the power plants. The generators encounter immense electromagnetic resistance, causing their rotational speed to slow down, which manifests as a drop in the grid's overall frequency. Conversely, if a sudden storm front pushes a massive surge of wind energy into the network when demand is low, the generators spin faster and the frequency spikes. Operators must relentlessly command power plants to throttle up or dial back their output to match consumption second by second. If the frequency deviates by even a fraction of a hertz for an extended period, it can trigger catastrophic resonance and severe overheating in heavy industrial machinery, prompting automated safety relays to forcibly disconnect entire power plants to protect themselves, resulting in a cascading failure that could plunge half a continent into a prolonged blackout. Historically, grid operators had a powerful physical ally in this balancing act: mechanical inertia. The traditional power grid was built entirely around massive spinning turbines inside coal, hydroelectric, and nuclear plants. These enormous steel rotors, weighing hundreds of tons and spinning at immense speeds, stored vast amounts of kinetic energy. When a sudden disturbance occurred, the sheer physical momentum of these heavy rotating masses naturally resisted any sudden change in speed, acting as a massive shock absorber that slowed down the frequency drop and gave the control room operators precious seconds to react. However, the 2026 transition toward a decarbonized grid presents a profound structural vulnerability. Solar photovoltaic arrays and modern wind turbines do not connect to the grid through massive synchronous spinning rotors. They connect through digital, solid-state power electronic inverters. Consequently, as older fossil fuel plants are retired and replaced by renewable energy, the grid is rapidly losing its physical inertia, making the frequency highly volatile and prone to sudden, violent swings. To avert a crisis of instability, the industry is widely deploying advanced grid-forming inverters. Older generations of inverters were grid-following. They passively measured the existing frequency using a phase-locked loop and simply injected current to match it, meaning they were entirely dependent on the grid already being stable. In contrast, the new grid-forming inverters utilize highly sophisticated model-based control software to act as independent, autonomous voltage sources. They do not follow the grid, they establish it. By utilizing internal virtual oscillators, these devices instantly inject or absorb massive amounts of power during a disturbance, artificially mimicking the inertial response of a heavy spinning turbine. This synthetic virtual inertia is essential to preventing blackouts in the increasingly weak, highly decentralized grids of the future.
Furthermore,
Modern control rooms are leveraging virtual power plants, seamlessly aggregating the power from thousands of residential rooftop solar panels, home battery walls, smart appliances, and connected electric vehicles via cloud software. By orchestrating these distributed energy resources as a single, massive entity, operators can inject capacity into the grid at a moment's notice to stabilize frequency, mitigating the need to build expensive new centralized power plants or conventional transmission upgrades. As the demand for energy outpaces local renewable capacities, the 2026 grid architecture is increasingly relying on the ultimate tool for ultra-long distance bulk power transport: high-voltage direct current transmission. While alternating current has reigned supreme for over a century, it suffers from a fatal flaw over extreme distances. The constant reversing of the current, back and forth, builds up massive reactive power losses and capacitance issues, limiting its practical reach, especially in underground or subsea applications. High-voltage direct current strips away the oscillation entirely, pushing the electrons continuously in a single direction. This provides two monumental advantages. First, the continuous push eliminates the reactive losses associated with alternating current, vastly improving the transmission efficiency and reducing the cost over massive distances. Second, because the current does not alternate, it does not have a frequency. This allows grid operators to construct massive direct current interconnectors between independent, asynchronous power grids, such as linking the disparate Eastern, Western, and Texas interconnections in the United States, or interconnecting European nations, allowing them to trade vast amounts of bulk energy without the impossible task of perfectly synchronizing their distinct alternating current heartbeats. This direct current technology has birthed the era of the global supergrid. In China, unprecedented ultra-high voltage direct current mega projects, such as the Changji-Guquan link, operate at a staggering 1.1 million volts. This colossal system spans over 3,000 kilometers, cleanly delivering 12 gigawatts of power, enough to supply 50 million homes. From remote northwestern wind and solar resources directly to the densely populated eastern seaboard, dramatically reducing regional coal consumption by tens of millions of tons. The ambition extends far beyond terrestrial borders, enabled by highly specialized cable-laying vessels that navigate the world's oceans. Massive ships, such as the Nexans Aurora and Jan de Nul's Fleming Jenkin and William Thompson, are equipped with split turntables and carousels capable of holding 10,000 tons of cable. Guided by advanced subsea technology, these vessels are currently orchestrating the installation of vast submarine power networks at depths reaching 4,000 meters, allowing for the integration of deep-water offshore wind farms. Recognizing the critical nature of this infrastructure, nations are moving to protect these underwater assets. The United States, for instance, introduced the Strategic Subsea Cables Act of 2026 to enhance diplomatic and physical security around these vital fiber optic and power links. These maritime operations make unprecedented international energy corridors possible. Groundbreaking ventures like the Australia-Asia Power Link aim to harvest intense solar radiation in the deep Australian outback using a 12,000-hectare solar farm, store it in the world's largest battery complexes, and push the electrons through a 4,000-kilometer submarine direct current cable directly into the power grid of Singapore, potentially supplying up to 15% of the city-state's electricity needs by the end of the decade. Similarly, the ambitious X-Links project intends to connect the Saharan sun and Atlantic winds of Morocco directly to the United Kingdom via 4,000 kilometers of subsea cabling. This project is specifically designed to bypass the intermittency of localized weather patterns, known as the Dunkelflaute, when European wind and sun are low, by linking disparate meteorological zones, providing continuous, baseload clean power. Look into the near future. The limits of material science are being pushed even further with the commercial maturation of superconducting power cables. by wrapping specialized high-temperature superconducting tapes in a cryogenic envelope of continuous liquid nitrogen, cooling the conductor to -200 degrees Celsius. Electrical resistance drops absolutely to zero. These advanced conduits can transport between 3 and 5 times the power of conventional cables through incredibly narrow underground corridors, offering a zero-loss solution to the severe spatial constraints of rapidly expanding metropolitan centers and power-hungry data center campuses, where building new overhead lines is hindered by public opposition and limited real estate. From the high vacuum isolation chambers of pristine substations and the mesmerizing violet glow of atmospheric ionization, to the white-knuckle helicopter maneuvers over icy mountain passes and the deep, silent trenches of subsea supergrids, the infrastructure of high-voltage transmission represents the pinnacle of modern applied physics. In an era where the demand for continuous, clean, and reliable energy has never been more intense, these invisible highways remain the absolute, indispensable backbone of industrial stability, seamlessly transporting the lifeblood of the global economy across the vast expanses of the planet.